going to talk about triangle groups. First, let's review some ideas from before. Here are some examples of what we called regular n-gons. Remember that these are polygons that have n vertices, where each side has the same length. We can denote a regular n-gon by simply looking at the vertices. In this case, let's denote the vertices as p sub k, where the p sub k's will lie equidistant along the unit circle. We can simply express this in terms of cosines and sines, as you see here on your screen. We're actually interested in the symmetries of the regular n-gon. That is, we're not really interested in all permutations of this set A because we wish to keep the point p sub k next to the points p sub k plus 1 and p sub k minus 1. We can put all of this together into the following result. Denote d sub 2n as the set of symmetries of the regular n-gon and circle as the composition of functions. Then we find a group with 2n elements. And in fact, this group is generated by just two elements, namely a rotation r, which is a rotation counterclockwise by an angle 2 pi over n, and the reflection s about the line y equals mx, where m is the slope tangent 2 pi over n. We also have the following relations, namely r to the n is the identity transformation, s squared is the identity transformation, and the commutator of r and s, namely r, s, r inverse, and s equals r squared. Another way to say this is as follows. Again, if we go back to considering the regular n-gon as simply the drawings that you have here on your screen, we can explicitly see that the generators r are the maps that send pk to pk plus 1, while s is the map that sends pk to p2 minus k. We can also think of R here in terms of a 2 by 2 matrix, which is just a rotation counterclockwise by an angle 2 pi over n. And S as the following 2 by 2 matrix, where S is just a reflection about the line y equals mx. And recall that m is just the slope tangent 2 pi over n. Today, we'd like to generalize these concepts. We'd like to generalize what we know about the cyclic groups of order n and the dihedral group of order 2n. So let's make the following abstract definition. Say that we have three positive integers m, n, and k. Formally, we'd like to define a group which will denote by delta of m, n, and k as generated by three types of rigid rotations, gamma 0, gamma 1, and gamma infinity. Here, gamma 0 to the m is the identity, gamma 1 to the n is the identity, gamma infinity raised to the k is the identity, and the composition gamma 0, gamma 1, gamma infinity is the identity. Such an abstract group is called a triangle group. We'll see why we're using the words triangle in just a moment. Here are a couple of examples. When m is 1 and k equals n, we find the triangle group is just Zn, the cyclic group of order n. On the other hand, when m and k are both equal to 2, we find the triangle group D sub 2n, namely the dihedral group of order 2n. For example, in the case of delta 1n, n, we can think of the cyclic group Z sub n as generated by the rotation r. In this case, we can choose gamma 0 to be the trivial rotation, gamma 1 to be the rotation r, and gamma infinity to be the inverse of the rotation r. Now it's easy to choose, or easy to see, the gamma 0 to the m, gamma 1 to the n, gamma infinity to the k, and gamma 0, gamma 1, gamma infinity are all equal to 1. For the dihedral group, let's recall that the dihedral group D2n is generated by a rotation r and a reflection s. In this case, we see that r to the n equals s squared equals the identity, and the commutator of r and s equals r squared. Here, to explain why we can view the dihedral group as a triangle group, let's choose gamma 0 to be the reflection s, gamma 1 to be the rotation r, and gamma infinity to be the reflection s circle r. In this case, it's easy to see, when m and k are both equal to 2, that gamma 0 to the m, gamma 1 to the n, gamma infinity to the k, and gamma 0, gamma 1, gamma infinity are all equal to the identity. Notice that Although we can express gamma 0, gamma 1, and gamma infinity in terms of the rigid rotations r and s, we can work conversely to express the rigid rotations in terms of gamma 0, gamma 1, and gamma infinity. For example, r equals gamma 1, s equals gamma 0, and the commutator of r and s is gamma 1, gamma 0, gamma infinity. Notice that the order here really does matter. The commutator, namely r squared, is gamma 1, gamma 0, gamma infinity, whereas we already know that gamma 0, gamma 1, gamma infinity is the identity. The following proposition explains that the notation is a little bit less cumbersome than it first appears. Delta of m, n, k is independent of the order of m, n, and k. Let's explain why. First, let's simply ease our notation a bit by substituting gamma 0 as s, gamma 1 as r, and gamma infinity as sr inverse. The idea is that because we have the product, gamma 0, gamma 1, gamma infinity is equal to the identity, really our group generated by 3 elements is actually only generated by 2 elements. Let's denote these 2 generators as r and s. They have not really any relation to the dihedral groups from before. We're just introducing 2 rigid rotations for our proof. In the middle of your screen, you can see now that we can write s equals gamma 0, r equals gamma 1, so that s times r is gamma infinity inverse. In this case, our triangle group, delta m n k, is generated by 2 rigid rotations, r and s, so that s to the m equals r to the n equals sr to the k equals the identity. We can actually express our generators r and s in terms of 2 new generators that we'll choose. Moving towards the top of the screen, let's introduce 2 new generators, u and v, by writing u as sr inverse, v equals s, so that u times v equals r inverse. In this case, we now see that our group, delta m and k, is actually generated by u and v that satisfy u to the k equals v to the m equals uv to the n equals the identity. But now, since our group is generated by u and v satisfying this relation, we see that actually this is the triangle group delta k m n. This means that delta m n k is actually equal to delta k m n. Now we've cyclically permuted m, n, and k to see that these 2 triangle groups must be equal to each other. Moving towards the bottom of the screen, we can do the same thing, but now for 2 new generators, we'll denote by z and w. Let's denote z as s times r, w as r inverse, and so that zw equals s. Now it's easy to check that z to the k equals w to the n equals zw to the m equals the identity. This means that our triangle group delta m n k is actually the same as the triangle group delta k n m. Here you can see we've simply interchanged m and k to find a new way to express the triangle group. But now one can check that all 6 different permutations of m, n, and k can be generated by some sequences of either a cyclic permutation or an interchange of m and k's. Let's continue by giving some more geometric examples of triangle groups. Say that we have positive integers m, n, and k, which satisfy the sum of the reciprocals equals 1. That is 1 over m plus 1 over n plus 1 over k is equal to 1. First, we'll define 3 angles, capital A, capital B, and capital C as pi over m, pi over n, and pi over k respectively. Next, let's define 3 affine points, capital P, capital Q, and capital R, in terms of the x and y coordinates you see here on your screen. And finally, let's define 3 transformations, gamma 0, gamma 1, and gamma infinity, rather explicitly as you see here on your screen. Don't worry so much about the explicit formulas. We'll explain in just a moment what these represent. We have the following properties. First, the sum of the angles is 180 degrees. That is, A plus B plus C equals pi. Second, these 3 points, P, Q, and R, form a triangle that has angles capital A, capital C, and capital C, respectively. Third, our transformations actually have a geometric interpretation. The transformation gamma 0 is a rotation counterclockwise around the point P by an angle 2 pi over m. The transformation gamma 1, on the other hand, is a rotation counterclockwise around the point Q by an angle 2 pi over n. And finally, the transformation gamma infinity is a rotation counterclockwise around the point R by an angle 2 pi over k. In fact, once you know this, it's then easy to check that the 3 transformations generate a triangle group corresponding to m, n, and k. Observe that this group is actually infinite and non-abelian. This is because if we consider gamma 1, gamma 0, we'll find that this is not the same as gamma 0, gamma 1. And actually, gamma 1, gamma 0 is a point of infinite order inside of our group. Next, we can use a Mathematica Notebook to try to explain a little bit more of what's really happening geometrically in this proposition. First, let's consider the case when m is 2, n is 3, and k is 6. In this case, the sum of the reciprocals is 1, and we find the triangle that you see here on your screen. We have a point P, which is at the lower left-hand part of your screen. This corresponds to an angle A, which is pi over m. That is, we simply have 90 degrees. We then have a vertex Q, which is at the lower right-hand part of your screen. This corresponds to an angle B, which is pi over n. In this case, this corresponds to 60 degrees. At the upper left-hand part of your screen, we have the vertex R. This corresponds to an angle C, which is pi over k, which is just 30 degrees. So the triangle here represents a 30, 60, 90 triangle. Now, let's take a look at what happened geometrically with gamma 0, gamma 1, and gamma infinity. Recall that gamma 0 is a rotation, in this case by 180 degrees, remember it's 2 pi over m, around the point P. Here, we can actually see geometrically how this works. Notice that we did rotate by 180 degrees. For gamma 1, we have now rotation by 120 degrees, and around R, that is our gamma infinity, we have a rotation by 160 degrees. Notice that we just had the composition of the 3. Let's see all 3 of those again. We had first gamma 0, this is rotation around the point P. We had next gamma 1, which is rotation around the point Q. And finally, we had gamma infinity, which is rotation around the point R. Here's the composition. First gamma 0, then gamma 1, and finally gamma 0. The composition goes back to where we had initially. You can actually see what we've done here is we've mapped out where each of the triangles go once we apply one of our elements from the triangle group. You can see the 1 inside of the yellow triangle represents that we haven't moved the triangle at all. We have gamma 0 at the lower left-hand part, which says that we've taken the triangle and now rotated around the point P by 180 degrees. We have gamma 1, which is the rotation of that triangle around the point Q by 120 degrees. And finally, we have gamma infinity, which is rotation around the point R by 60 degrees. You can now see what happens if we have various combinations of these triangles, of these various operations from the triangle group. This simply moves around the triangles and gives us a tessellation of the plane. Let's take a look at another example. Let's take a look here when we have m is equal to 2, n is equal to 4, and k is equal to 4. This is a 90, 45, 45 triangle. Around the point P, we're going to rotate by 180 degrees. Around Q, we'll rotate by 90 degrees. And around R, we will rotate by another 90 degrees. Now let's take a look at gamma 0, circle gamma 1, circle gamma infinity to get back to where we started from. So this here is really just a way to check that really there is a geometric interpretation of the various identities we have in our triangle group. As another example, let's consider when m is 3, n is 3, and k is 3. So now we have a 60, 60, 60 equilateral triangle. Here we can rotate around the point P by 120 degrees, around Q by 120 degrees, around R by 120 degrees. And now let's consider the composition gamma infinity, circle gamma 1, circle gamma 0. And we see that we get back to where we started from. Notice that there are only finitely many positive integers m, n, and k, such that the sum of the reciprocals is 1. And you can check that this list here is exactly the 3 that we talked about before: 236, 244, and 333. In fact, by looking at the example that we did discuss before, you can see that we can continue in such a way that we can actually have a tessellation of the entire plane by using these types of triangles. We're using the word tessellation, but we can also use a tiling of the plane. Sometimes we call these three groups wallpaper groups because they're exactly what you would find in patterns involving wallpaper. Here we see that we can just simply write out the entire plane, or if you will, our wall, as being tiled by a collection of triangles. The triangles either being 30, 60, 90, which we call the kiss rhombile, 45, 45, 90, which we call the kiss quadrile, or 60, 60, 60, which we call the deltile. Here are even more examples of all of this concept. Now, we've only really focused on integers where the sum of the reciprocals is equal to 1. But what if this is not the case? In fact, our triangle groups will be much more interesting when the integers are a bit different from what we had before. For example, we've already seen that for the cyclic group, Zn, we can consider 1, n, and n. And for the dihedral group, we can consider 2, n, and 2. In fact, notice that in both of these cases, we have the sum of the reciprocals is strictly greater than 1. In fact, we're actually going to use this to study triangles that instead of drawing in the plane, we can actually draw on the surface of a sphere. So let's try to write the same proposition as before, but now by drawing our triangles in 3 dimensions. Let's say that we have positive integers m, n, and k, where the sum of the reciprocals is greater than 1. We'll consider the same angles as before. A is pi over m, b is pi over n, and c is pi over k. But now we're going to draw 3 points, P, Q, and R, in terms of the coordinates, the x-coordinate, the y-coordinate, and the z-coordinate. And we're going to introduce 3 types of rotations: gamma 0, gamma 1, and gamma infinity. Again, don't worry so much about memorizing these formulas. This is all written out explicitly so that we can make the following statements. First, the sum of the angles is greater than 180 degrees. That is, A plus B plus C is greater than pi. Second, these 3 vertices, P, Q, and R, generate a spherical triangle whose angles are A, B, and C. Third, similar to before, the rotation gamma 0 is a rotation around the point P by 2 pi over m, gamma 1 is a rotation around Q by 2 pi over n, and gamma infinity is a rotation around R by 2 pi over k. These 3 rotations, gamma 0, gamma 1, and gamma infinity, form an example of a triangle group. Let's go back to the cyclic group and dihedral groups to take a look at some pictures to understand what's really going on here. Well, let's go back to the case where we have 1, n, and n, but let's generalize this just a little bit. Say that at least one of m, n, and k is equal to 1. Perhaps lowercase n is equal to 1. Then our triangle group, delta m, 1, and k, is just simply delta of n, 1, n, where capital N is the greatest common divisor of M and K. So we might as well consider the special case when M, N, and K is equal to capital N, 1, capital N. In this case, the delta that you see at the top of your screen is equal to 0. So we actually have an isosceles triangle that we've drawn on the surface of the sphere. This is a slightly odd looking triangle because one of the three angles, capital B, will just be equal to 180 degrees. Such a region is actually called a lune. In this case, we'll think of it as a degenerate type of a triangle. The cyclic group in this case is generated by gamma 0, gamma 1, and gamma infinity, but notice that gamma 1 is the identity, whereas gamma 0 is a rotation around the North Pole P by 2 pi over n, and gamma infinity is a rotation around the South Pole by 2 pi over n. What we'll do here is we'll try to give each of our triangles a slightly different color so we can see what's happening here. In this case, the corresponding figure that we'll find will be called a hosohedron. Here are some examples. Each of the red triangles is an example of the triangle PQR that we started with. You'll notice that as we take a look, here we have the red regions really are degenerate triangles. Two of the angles are pi over n, whereas we have a third, which is actually 180 degrees. So the angles here look a little bit weird, which is why these are really hosohedron, or if you will, beach balls. But really we call these red regions lunes, as opposed to calling them triangles. Lunes, as in it does look like it's part of a crescent moon. You can also see how the rotations gamma 0, gamma 1, and gamma infinity come into play. Gamma 0 corresponds to a rotation at the North Pole, whereas gamma infinity corresponds to a rotation at the South Pole. Gamma 1 really is a rotation around the equator, but we're going to ignore it because it's a rotation that's just the identity rotation. Similarly, let's take a look at the case when n and k are both equal to 2. Now we'll introduce dihedral groups. Here, we can form a triangle according to points P, Q, and R, where one of the angles is pi over n and the other two are 90 degrees, pi over 2 and pi over 2. In this case, we do find the dihedral group where gamma 0 is a rotation at the North Pole by 2 pi over n, and gamma 1 and gamma infinity are actually rotations in this case by 180 degrees. That is, gamma 1 squared is the identity, and gamma infinity squared is the identity. Just like before, we can try to give a different color to each copy of the triangle, but in this case, the figure that we'll find will be called a bipyramid. Here are some examples. Remember that the red regions are our triangles. Notice that we have, for each red triangle, a vertex at the top. This is the vertex P, and gamma infinity is just a rotation by 2 pi over n. Around the equator, we have our points B and C, Q and R, and the angles B and C both correspond to 90 degrees. This is why along the equator, we can rotate by 180 degrees. This will be our gamma 1 and gamma infinity, respectively. Here you can see that the groups that we find really are the dihedral groups. Finally, is there a way we can tile the sphere in other ways? Are there some examples that we're forgetting about? Here's where we'll introduce the Platonic solids. Think of these as a three-dimensional generalization of the regular n-gons. Here, instead of plotting out points on the unit circle, making sure that these vertices are equilaterally spaced, now we'll try to plot these in 3 dimensions so that we're plotting them on the surface of a sphere. And just like before, we want to make sure that our points are equidistant, that they're equally spaced. There are only 5 Platonic solids, and they are named after the Greek mathematician Plato. Here, on the screen, you can actually see a little bit more information. These 5 Platonic solids are called the tetrahedron, the cube, octahedron, dodecahedron, and icosahedron. Here we've written out how many vertices, edges, and faces each of these Platonic solids has. As mentioned before, there are only 5 Platonic solids, and actually we can pair these off. For example, the cube and the octahedron are duals of each other, whereas the dodecahedron and icosahedron are duals of each other. What we mean by dual is, if you consider the replacing the midpoint of a face with a vertex and a vertex with a face, then you can look at the dual Platonic solid. Platonic solids only have 3 types of symmetry groups. For the tetrahedron, the symmetries are the alternating group A4. For either the cube or the octahedron, the symmetry group is S4. And for either the dodecahedron or the icosahedron, the symmetry group is A5. Recall that for the regular n-gon, the symmetry group is the dihedral group D2n. Each of these symmetry groups is an example of a triangle group. We can actually express these groups in the form delta 2, 3n, where if n is equal to 3, we find the rotations of the tetrahedron. If n is equal to 4, we find the rigid rotations of either the cube or the octahedron. And if n is equal to 5, we find the rigid rotations of either the dodecahedron or the icosahedron. Moreover, if m, n, and k are positive integers such that their reciprocal is greater, the sum of the reciprocals is greater than 1, then the triangle group is either a cyclic group, Zn, dihedral group, D2n, or one of the rigid rotations of the Platonic solids, either A4, S4, or A5. Let's try to explain geometrically what's going on here. Recall that the symmetric group S4 is the octahedral group, whereas the alternating group A5 is called the icosahedral group. As we just said, in general, our groups delta M, N, K, where the sum of the reciprocals is greater than 1, are examples of polyhedral groups. These are the groups that we get by either the rigid rotations of the regular n-gon or the rigid rotations of a Platonic solid. Here's a chart to kind of keep in mind what's actually happening. Recall that for either the cyclic group or the dihedral group, we explained how we can draw a triangle on the surface of a sphere such that we either find a hosahedron or a bipyramid. In fact, the triangle group is literally the rotations of the red triangles that we found before. This is actually why we call it a triangle group. Using the same constants as before, we can consider an angle A, angle B, and an angle C corresponding to pi over m, pi over n, and pi over k. This would then give us triangles P, Q, and R, just like the formulas from before, and we see that we can find triangles such that the tessellation, or if you will, the tiling, will give us back either A4, S4, or A5. Again, we simply just draw the triangles, and now we connect them according to gamma 0, gamma 1, gamma infinity. We can consider these triangles and now try to draw them to see what happens on the surface of a sphere. Here are the pictures. On the very left, you can see here we have a 60, 60, 90 triangle. This corresponds to m equals 2, n equals 3, and k is equal to 3. Indeed, stare at a black triangle on the lower left. You can see that the angles of these triangles are indeed 60 degrees, 60 degrees, and 90 degrees. Another way to see this is that there are 2 black triangles at one vertex, 3 black triangles at another vertex, and 3 black triangles at the third vertex. This is where you can visually see the 2, 3, 3. In the middle, you can see where it corresponds to S4, namely M, N, and K being 2, 3, and 4. If you stare at one of the black triangles, you can see that one vertex has 2 black triangles attached to it, the other one has 3 black triangles, and the final one has 4 black triangles. And finally, for the one on the lower right, this will correspond to A5. You can see that this will correspond to M equals 2, M and N and K being 2, 3, and 5. Again, if you stare at one of the black triangles on the lower right, you see that one of the vertices has 2 black triangles surrounding it, another one has 3 black triangles surrounding it, and the final one will have 5 black triangles surrounding it. So these are 3 different ways we can tile the sphere, and surprisingly, these are the only ways and we can tile the sphere. This is because the only integers that satisfy the sum of the reciprocals is greater than 1 would have to be exactly one of the numbers you see here on your screen. Thanks for watching.